Thank you, Chris, for the introduction and for the invitation to open this. Sorry, I'm trying to manage the windows that are sticking in front of my presentation. Yes, so the introduction, you've given me the choice and you've given me the opportunity to introduce the series of examples and ideas that we want to put across in today's training session. Now, I could have told you about what the Copernicus Climate Change Service is and how it sits at ECMWF, but I've chosen to do something else. In the more than 20 years I've worked in seasonal forecasting, I've come to realize that it's always a surprise to see the point at which people come to seasonal forecasts. So just to make sure that we are on an equal playing field, I want to go back to basics and just bring forward some ideas. I will not demonstrate anything, I will not explain anything in great depth, but I just want you to remember all these things which you probably all know. Having said all that, I don't know who's in the audience. I've not had the opportunity to find out the background of the audience. So some people might know all of this, might find it tedious, but for which I apologize, but it's only 15 minutes. So I will not waste any more time. I want to go through firstly, the most important thing I might want to do at this point is to just remind people about how can we even hope to predict things on timescales longer than a few days. You'll all remember the business of chaos, and you all probably have dealt with the concept of predictability. I want to show you just an illustration which takes you very far away from models and maps and the like. This is a pinball table. You probably know you throw balls to the top and they bounce amongst these pins, which represent the chaos, the effect of chaos, and they end up falling at the bottom of the table through one of these slots. And the more you throw many balls one after the other, and you will find that after, if the whole thing it's set fairly, you will end up with most balls in the middle, fewer than in the middle, but roughly the same numbers immediately next to the middle, and fewest at the ends. So the precise ball in which a single ball, so the precise bin in which a single ball falls cannot be predicted. But if many drops are made, then the distribution of balls in the bins can be described as I have here. Think of this as precipitation in individual years, in individual seasons, and think of the distribution here as to the left is dry, to the right is wet. Now, as I said, you can't say much more than this. But what if you were to push the table to the side? Can you say anything about the distribution that will be achieved then by doing exactly the same thing once again? I've left the green in place from the previous exercise. Now I ask you to believe me that if I throw the ball, it would probably end up in a distribution that looks much more like the blue lines. So by tilting the table, I have managed to change the shape of the distribution, but I still cannot tell you which precise bin an individual ball throw will end up. The tilt of the table changes the shape, and the new distribution can again be described if you throw sufficient balls. Now, let's come back to the forecast and think of this as the paradigm we face in a forecast. The green would be the climatology. Nothing's moving, nothing's changing. I have lots of realizations, and that's what I do know about this phenomenon. When I push the table is I could think of this as an individual forecast or a number of individual forecasts, all of which have the same starting point. Because of the chaotic bit in the middle, I'm not still going to be able to say where the individual ball falls through. So remember this because while everybody wants a deterministic forecast, wants to know what's going to happen, and has been brought to become familiar with deterministic forecasts for weather timescales, as soon as you go much further into the future, chaos starts to play a role, and you can no longer say the same thing. So in a seasonal forecast paradigm, the prediction consists in a difference between the two distributions. Effectively, this is managing your expectations as to what you might ever be able to achieve with a seasonal forecast. Now, what can push the table? Let's call it large-scale influences. What would I mean by that? Well, for example, a persistent pattern of ocean temperatures. This is, again, nothing new. But I want you to, again, I like to use this example because it allows me to remind you that you can push the table with one pattern, but other things will influence as well. And they will also push the table, and they may push in the same direction as my sea surface temperatures do here, or they may push in the opposite direction. The question as to which wins and what's going to happen in the end, it's the thing that the models try to resolve. Now, just to give you another pointer for a reminder, this is an example of sea surface temperatures in 3 consecutive months, December, January, and February. And I put this up so that you can see that the pattern is large scale. You could have seen that in any map of sea surface temperatures you draw at any time. The patches of red and the blue, which means colder or warmer than average, are large scale. But also you can see that they don't change very much. These two are in the same year, so they are consecutive time steps. Because these things are slow varying in time, is why we can actually hope to predict what happens in the atmosphere, which comes into contact with this ocean. So this is the whole principle of how we get predictability. Some components of the climate system change slowly enough for us to be able to either model the change or assume that it stays roughly constant from the initial conditions. And those effects, those patterns do affect the atmosphere, come into contact and affect the atmosphere. Now, this pattern here, for those of you who've seen these things, is a La Nina event. So I decided to show you what the typical, a map that shows the schematic, very simple schematic of what the typical effect of La Nina is, and to draw your attention back to the fact that the impact is also large scale. So you don't expect things to happen very differently at different locations to first order. Primarily because of the large scale of the forcing or driving pattern. Now, a couple more reminders. How do people normally do long-range predictions? By long-range, here I mean seasonal, interannual, multi-annual, or even sub-seasonal. Well, traditionally, people have used statistical methods, and returning back to this particular paradigm, this is all about using empirical relationships derived from his historical record. What statistical methods you use is the first thing that distinguishes the old-fashioned empirical forecasts from the current machine learning techniques, I would argue. Or you can have dynamical models where you use dynamical climate models, the dynamical methods. What do I mean by dynamical forecast system? And maybe the speakers after me will make reference to this. Well, a forecast system includes a model, includes a definition or description of the starting point, the initial conditions, which involve data assimilation, and also needs to describe the uncertainties in the expected outcomes. We'll talk in a minute about where those uncertainties might come from. Well, here, now, immediately. We also need to use ensembles because uncertainties in the initial conditions amplify sufficiently much through the forecast integration that in the outcome of the forecast, the uncertainties tend to be larger than the initial conditions. You also get uncertainties not just from the initial conditions, but from the model formulations. I remind you that even though dynamical methods do solve equations of classical mechanics, they do not solve them exactly. So there are approximations, and depending on how you make these approximations, different models might have different, might lead to different uncertainties. So just a quick schematic. Let's imagine that is the area in which I can describe, I can confine the uncertainties initial state. I run a model, I run it from several initial conditions that are consistent with this uncertainty, and I end up in an area in the outcome space which is typically larger than the beginning. This is the uncertainty in the future atmospheric state due to the initial condition uncertainty. But now I said I want to illustrate the model uncertainties as well. So what do I mean by here? Let's think of the multi-model concept. I have model A just like before, and I run it so as to explore the effect of the uncertainties due to initial conditions uncertainty. But I also have a model B. Let's start it from the same initial conditions. Likely as not, more likely than not, probably you will end up in a completely different part of the space. And that is because the different models will propagate the uncertainty initial conditions sampled in exactly the same way in a different place. This is what I would refer to, roughly speaking, as a multi-model. And arguably, the uncertainty in the future atmospheric state will end up being larger than that would be described just by a single model. But what if I don't sample the uncertainty in initial conditions in the same way? So I have the same space, I have the same initial conditions, the uncertainties arguably are the same, but the two models now start from different initial conditions. They may have other things in which they differ, not just the formulation and the sampling of the initial uncertainty, but they will now result possibly in a yet larger, certainly different uncertainty in a future atmospheric state. Now, knowing that different models are formulated somewhat differently, and they might convert these uncertainty from initial conditions into that in the future state in a different way, makes it important to represent the model formulation uncertainties in your estimates of what might happen. I refer to this as multi-system, and you'll find repeatedly on our website and in our presentations the reference to multi-system as opposed to multi-model. By that, I want to remind people that it's not just a model that changes. There are lots of things that are different between the components of the multi-system. One last point before I get to very close to the end. Let's remember what is predictable at long range. It is not the weather at a specific location at a specific time. It's what we refer to as climate. We predict a range of outcomes with probabilities attached to them, and because of what I showed earlier, we tend to look at large area averages, not local details. Just a quick example about again to maybe just anchor the language that we'll be using in a moment. Again, you're probably familiar with the concept. Here I'm showing you the model runs for a particular thing. It really doesn't matter what years, what models, or anything else. The black line is the observed climatology. So this is an average for the months of May, June, July, August, September, so on, of some region, of sea surface temperature in some region. And as you see, that doesn't vary very much in time. I have run the model with these over this period with the initial conditions as described by the historical record, accounting for the uncertainty. So I've run ensembles in each year, 8 ensemble members per year, and I have 14 years worth of runs here. So the brown lines are all forecast initialized from past dates, what I tend to refer to as hindcasts, but you'll hear others refer to as forecast. Now, if I average these realizations, which effectively represent the climate of the model, I'll end up with a very different line from the black line of the mean climate of the observations. By the way, all these things are real numbers, and all these things are done in the way you would do it in a real forecast system. Now, there is a systematic, there is a difference. There is a large difference in places, very large difference in places. And I would argue it's a rather systematic difference. Pretty much all ensemble members start and then they go colder than the observation that the observed climatology might tell them. So let's just strip away the individual ensemble members and remember the two lines. They're again the same lines as before. I've just changed the scale on the y-axis. The observations are in black, and the hindcast mean that the blue line from here is now left by itself. Now I make a new forecast. I have a number of ensemble members, 8 again, and I can look at the ensemble mean, which is a very attractive proposition for many people many times. And if I just look at the forecast and I compare it to the observations, I say, well, this is a forecast for a colder than average situation. In this case, we are looking at Nino indices. This is a La Nina event. But then I remember the forecast comes from the model. And I remember the model has a tendency to go cold every time I run it. And in fact, if I look at the hindcast mean, I see the model climatology is actually colder than the members in the current forecast. So then if I interpret this correctly, which is what I absolutely must do, this is a forecast in effect for warm anomalies, which would be an El Niño event. So at long range, you need to predict anomalies, whether it's anomalies in amplitudes of ensemble mean or ensemble members or probability space. You need to refer everything to the model climatology. Right. To close, the C3S forecast multi-system, I didn't want to dwell much on this because you can find all this in our documentation on our website once you want to engage with it. It's a setup that's been operational since 2017, a year after the Copernicus Climate Change Service started its activities. It was built as a successor to the EuroSIP multi-system European endeavor, which in its early days contained 3 models, 3 participants. Later, it added 2 non-European ones, the US and Japan. Enhancing on this, we now have a multi-system that has 9 components. In May 2025, the 9th contributor joined. So these are the logos. I hope they're big enough and you can recognize them all. I'm not going to read them out. We have these 9 components. Now, I'm not going to indicate that you must use all the 9 components every time you make a decision. But this data is there, and as I tried to persuade you earlier, looking at more than one model makes sense and adds value. I don't have any explanation and any illustration of skill and how much better you do if you use a combination than if you use individual forecast systems outputs. But Chris will tell you later today, Chris Goddard will tell you later today about how to persuade yourselves of this. All contributors to the C3S multi-system are WMO Global Producing Centers of Long-Range Forecasts, and you can probably find equivalent forecasts from them at the WMO Lead Center's website. But here we offer a lot more variables than you will find there at higher temporal frequency, and hopefully some facilities and tools and materials that will help you reformulate, reinterpret the outputs in a way that suits you best. What I also want to say, and I don't have a slide to this effect, is the fact that you will find some graphical products. Well, no, I have a slide about this. What you'll find on the C3S website is data products on the website and, sorry, on the climate data store, which will be made clear to you in a moment. And you will find some graphical products that we have formulated. The climate data store includes a large number of atmospheric variables. It includes some ocean variables. For the atmospheric variables, we have daily and sub-daily data. We create some monthly statistics and the monthly anomalies. As I said, we wanted the first order correction of that bias, that systematic difference to be done in some way. But this is not necessarily the only way to do the bias correction. So while this is a ready-made thing you can use from the website, from the database, also you can take the daily or the values from the forecast themselves, because we also offer all the hindcasts that go with those particular forecasts. So you will find all the data you need there to make proper use of the individual real-time forecast. Real-time forecasts are published every month. We collect the data that has been obtained with model runs initialized around the 1st of the month. Again, I'm sure that we will find out in a minute more about the different initialization strategies and how that has implications for the data you might find. The publication date for real-time forecast is the 6th day of the month for ECMWF data and the 10th for the rest. It's all to do with data policies and the time it takes us to take the data from the external contributors and bring it in. Now, with this data, we do create some graphics, and these are just one way, sensible way, well judged way to create some products and some diagnostics. It is not the only way, so do not regard it as the definitive thing. We don't do any high-level calibration, any bespoke calibration. A lot better probably could be done if you interpreted the data in the context in which you need to use it. We have a relatively small subset of the variables that we offer as data in the graphical products. You can go and browse. The interface is quite nice to browse, and it's quite easy allows you an easy comparison and an easy side-by-side view of the individual solutions, as well as look at the combinations. We have some skill scores that we publish in the verification page, and you can check the skill not just of the individual components, but of the combination we have used. But I must stress, in all these things, you are going to see the answer to the choices we have made in this particular combination. I'll stop here and look forward to hearing what my colleagues have to say beyond this. Thank you.
Thank you very much, Anca. Are there any questions for Anca? We should try to keep it brief because we're a little bit behind schedule. I don't know if anyone has, I don't see any.
I'll stay around, Chris, afterwards. If somebody thinks later to ask any questions, I'll be around.
Great, perfect. Or if anyone has any questions they'd like to put in the chat, we can also collect that and answer that and get back to you. I don't see any hands up. I guess also people need to be warmed up a little bit before they start asking questions. But I would go straight to the next presentation. And then if there are any questions, we can take